cube contain? 0. Does it cover the set? It does. Can you get smaller than 0? Adding up adding up positive things? You cannot. Therefore, the exterior measure of a point is 0. Great, we proved it. That's probably all I'm going to prove. But he does have a proof for example 2 and 3, which is rather detailed and not that hard to understand. He says the exterior measure of a rectangle is equal to its volume. That's example 4. All right. The exterior measure of all of RD is, what do you think? Infinity, right? And example 6, the exterior measure of the Cantor set is 0. So, his argument is basically that M star C is less than or equal to 2 over 3 to the k for all k. That's how he proves that. All right, so these are all examples of the exterior measure. All right. Now he proceeds to make a series of observations. All right. Well, I mean technically a finite sequence. But a finite sequence of observations. Let me make them as well here. This Cantor set does seem a lot like that paradoxical triangle I wrote.
I think if you can have like a function that maps every point on the side of the triangle down to the hypotenuse, like something kind of like.
There's that Sierpinski carpet or something. All right, so observation 1 is monotonicity. Hard word for me today. But it simply means that E1 subset of E2 implies that the exterior measure of E1 is less than or equal to the exterior measure of E2. Of course, in the extended sense of inequality, infinity is larger than what numbers? Countable subadditivity. It says that if E is equal to the union, j equals 1 to infinity of Ej, then the exterior measure of E is less than or equal to the summation, j equals 1 to infinity of the exterior measure of Ej. Observation 3, if E is a subset of RD, then M, the exterior measure of E, is equal to the inf of M star of O, where, well, let me just write it plainly. It's the inf of M star O such that O is open and E is contained in the open set. Observation 4, it says that if E is E1 union E2, and the distance from E1, what's the distance between sets? What does that mean? Sam. How would you guys define the distance between, say, a sphere and a cube? What if they intersect? If I would say if two things intersect, the distance between them is 0. So if they don't intersect, I would say that the distance between them is, I would say it's the smallest distance that you can find between 2 points on them, right? But that won't quite work because sometimes the edge is fuzzy, so that smallest point isn't actually actualized. So you take it to be the inf of all possible lengths connecting points in the two objects. Like take a point x in the one object, take a point y in the other object, take the inf of the displacement from x to y as x and y are taken from one over one set and the other. That would define distance. But this makes a lot of sense, right? Because if the distance between, certainly if the distance is greater than 0, that means that they're disjoint, right? So this is encouraging that, not encouraging, I can't write my stars. Star. So, observation 3, observation 4, observation 5. So what do you think about all these observations? I think it means that the exterior measure is, well, among other things, behaving like a measure, right? I mean, it's doing some of the things we wanted, I think. Ah, the translation, yeah. Let's see here. He says this last property shows that if a set can be decomposed into almost oh, and I've forgotten something here. These are what are these? These are almost disjoint cubes, guys. I should have written that. I'm sorry. I didn't even say it. I meant to. Almost disjoint cubes. So if E can be written as a countable union of almost disjoint cubes, then the exterior measure of E is the sum of the volumes of said cubes. He says the last property shows if a set can be decomposed into almost disjoint cubes, its exterior measure equals to the sum of the volumes of the cubes. In particular, by theorem 1.4, we can see that the exterior measure of an open set equals the sum of the volumes of the cubes in a decomposition and coincides with our initial guess. Moreover, this also yields a proof that the sum is independent of the decomposition. Right? Does the exterior measure depend on, I mean, this is over all possible coverings, right? So it wouldn't matter the particular. Again, this is outside in. Theorem 1.4 was inside, wasn't really inside out. It was from the inside to the edge, right? So if you look at the proof of theorem 1.4, it's fitting cubes inside the thing, kind of eking up to the edge, whereas the exterior measure starts at the outside and kind of squeezes in. They're dual ideas. All right. He says, one can see from this that the volume of simple sets are calculated by elementary calculus, as calculated by elementary calculus, agree with the exterior measure. He says this assertion can be proved most easily once we've developed the requisite tools in integration theory. That would be the next chapter. But he warns that even for, if you take disjoint subsets, there exist disjoint subsets, E1 and E2. It's like E1 intersect E2, non-empty. Yet the exterior measure of the union of E1 and E2 is not equal to the exterior measure of E1 plus the exterior measure of E2. This is somewhat disconcerting. And I think, he doesn't reference a homework exercise there either. I wonder how bad that construction is. I don't really care. All right, so this brings us to section 3 finally, which is the definition of Lebesgue measurable. So I'll write down the definition for us, section 3. Which is measurable sets. Measurable sets. And Lebesgue measure. I'll start with the definition. E, a subset of R, D, is Lebesgue measurable or simply measurable if for any epsilon greater than 0, oh man, not this again, there exists there exists an open set with E contained in the open set and the exterior measure of the complement of the open set by E less than or equal to epsilon. He says this should be compared to observation 3, which holds for all sets E. I think what he's saying is that the definition is motivated by observation 3 in some sense. Now, if E is measurable, all right, we define its Lebesgue measure or measure to just be the exterior measure. In this case, M of E is equal to M star E. So we're using this exterior measure to define the Lebesgue measure. All right? Now, let's see here. What would this picture mean? I mean, if we took, for example, well, suppose our E was the open set from A to B, right? And suppose we said that epsilon was, a quarter. Let's be more specific. Let's say 1 to 3, right? That open set. And if we look at epsilon equal to, I don't know, a quarter, right? Then what open set could I find which would surround say 0.9 to 3 point what? 3.15? All right. And then what's the, if we take that to be our O, then what's the complement of E by O? Yeah, so then this minus E is 0.9 to 1 included, unioned with 1 to 3.15, or 3 to 3, right? 3 to 3.15. And the measure doesn't care about endpoints. You can work this out. The exterior measure doesn't care about endpoints. And the exterior measure of that is indeed 0.25. You guys cut it awful close, you know? Like you could have given me, you know, something like 0.9 and 3.1. You know, then the exterior measure of the open set, which covers it, complemented by E, would have exterior measure 0.2. You've made it so that the complement of O by E has exterior measure 0.25, which is exactly. But you can. So the point is, if you can do this for arbitrary epsilon, then that makes the set E quote unquote measurable. And then we already have defined the exterior measure of E in terms of being the inf of all countable collection of cubes, the volume of all countable collections of cubes which cover it. Yeah. So that's the definition of Lebesgue measurable. I will read for you now the rest of the results in the section. I'll probably write them down on the board next time, but you know, property 1, every open set in RD is measurable. Property 2, if the exterior measure is 0, then E is measurable. In particular, if F is a subset of a set of exterior measures 0, then F is measurable. So any subset of the Cantor set would be measurable. A countable union of measurable sets is measurable. Closed sets are measurable. So we've got open sets are measurable, closed sets are measurable. Remember, this is open and closed with respect to metric topology, not like your favorite weird topology in RD. Lemma 3.1, if F is closed and K is compact and these sets are disjoint, then the distance from F to K is greater than 0. This is a lemma. He uses that to then prove property 5, which is that the complement of measurable sets is measurable. So if I have E is measurable and I look at RD complemented by E, measurable. Countable intersection of measurable sets is measurable, right? And then he proves theorem 3.2, if we have a bunch of disjoint measurable sets and E is formed from their countable union, then the measure of their countable union is in fact the sum of their measures. So, what he says, this result provides the necessary connection between the following: our primitive notion of volume given the exterior measure, the more refined idea of measurable sets, and the countably infinite operations allowed in these sets. Then a really beautiful notation is introduced we'll talk about next time. And then at the very end of this section, he talks about the invariance properties of Lebesgue, and we'll talk a little bit about the sigma algebras and the Borel sets in this context. And then on page 24 to 25, and this I will probably not cover, but he constructs a non-measure. You might start to think, is there anything that's not measurable? Right? It seems like everything is measurable. Something as weird as the Cantor set's measurable, right? Is there anything that's not measurable? Yes. And that's what pages 24 and 25 do, is they build this horrible, really, really weird set which is not measurable. And then hopefully next time we meet, we'll talk about things I just talked about briefly. And then we'll go on to describe what are measurable functions, which is the end of this chapter.
Are we meeting on Friday?
We'll meet on Friday, yeah, but not Wednesday. And then we also, I will not be here next Monday, so you'll have that day off.
I won't be here Friday.
You won't be here Friday?
I'm going to an undergraduate conference.
An undergraduate conference. Oh, well, that sounds exciting. So anyway, all of this culminates with Littlewood's three principles, which says every set is nearly a finite union of intervals. Every function is nearly continuous. And every convergent sequence is nearly uniformly convergent. So it's like this example I put on the board to start with. It's almost right, except for that one point, right? That can be made formal with the terminology which is introduced in this chapter. The idea of almost everywhere, which we'll talk about next time. Almost everywhere is not like, you might get the impression that when you hear a mathematician talk about something being true almost everywhere, that they don't really know what they're doing. It's actually the opposite. It's a precise technical phrase which has a specific nuanced meaning. So, which I think out of context, my brother and I were talking about this, how like out of context it makes people who know what they're doing sound like they're like just making stuff up, you know? Which is sometimes true, but anyway.